are aware of the uses of radio waves for communication, microwaves for cooking, and X-rays for medical imaging. In this series, we are primarily concerned with the uses of X-rays in diagnostic radiology to produce images. You should, however, be aware of the other uses of the electromagnetic spectrum in medicine, such as radiation therapy, transillumination, thermography, and nuclear magnetic resonance imaging. In radiation therapy, high-energy gamma rays located at the top of the electromagnetic spectrum, as shown on the upper right of this visual, are used to destroy cancer cells. The gamma rays penetrate to the depth of the tumor, depositing enough energy to destroy tissue. Number 21. At the visible light level of the electromagnetic spectrum, as shown at the upper right, the process of transillumination uses visible light to penetrate certain structures within the body. Examples of the structures examined using this process are breast tissue and skulls of newborns, as shown here. On the left is a side or lateral view, and a frontal view is shown on the right. These structures transmit enough light to permit useful diagnostic information to be obtained. The infant on the right shows the characteristic signs of hydrocephalus, or water on the brain, while the infant on the left is normal. Number 22. This photo was taken with radiation from the infrared portion of the spectrum, located just below the visible light portion. The human body emits infrared radiation. We do not perceive this radiation as light because infrared radiation is outside the visible range of the electromagnetic spectrum. It has, however, been observed that disease or injuries cause a change in the pattern of infrared radiation emitted by the body. In a technique called thermography, a special camera records the infrared pattern emitted and displays it using a color scale. In this visual, the reddish-brown areas indicate regions of chronic pain in the patient's hands. Number 23. At the bottom of the electromagnetic spectrum, as shown on the lower right, radio waves are used to obtain information from within the body in NMR, nuclear magnetic resonance imaging. Also called magnetic resonance imaging, or MRI, this technique uses a large magnet to align nuclei in a patient. Radio waves are then beamed into the patient. Almost immediately, the nuclei re-emit the radio waves. Since the nuclei are aligned, the waves combine to produce a signal that can be detected, analyzed by computer, and displayed as an image. A recorded NMR image of a skull is shown on the lower left. Number 24. You are now ready for Review Exercise A in your student workbook. When you have completed the exercise, turn to the answer page at the end of the review exercise section and check your work. Then restart the tape. Stop the tape now. You should have completed Review Exercise A and checked your answers. If your score is less than 80%, you should review this material before proceeding to Section B. A score above 80% deserves congratulations. It indicates that you are mastering the material. Please rewind this tape so that it will be ready for the next person to use. Thank you. Multimedia Publishing Incorporated of Denver, Colorado presents Section B of Lesson 6 in the Radiation Physics series. You should now have slide number 25 in view and be ready to proceed with the audiovisual presentation. In Section B, we examine the basic interaction of X-rays with matter. When you have completed Section B, you will be able to define the terms primary radiation, attenuation, and remnant radiation. Describe coherent scatter, photoelectric effect, Compton effect, and pair production. And name the three factors that determine the probability of photon interactions with matter. Number 26. Here are 4 X-ray photons produced by an X-ray tube that are about to enter a patient. These photons are meant to represent the billions of photons that make up the X-ray beam before it strikes a patient. These photons are referred to as primary photons. A sheet of film is shown below the patient. In the following slides, we examine the fate of the primary photons, some of which pass through the patient and strike the film. Those that strike the film are responsible for the radiographic image. Number 27. In our example, one of the primary photons ceases to exist somewhere inside the patient. All of the energy of that X-ray is transferred to the atoms and molecules of the patient. Therefore, that X-ray will not strike the film. This process is referred to as absorption. Number 28. A second X-ray photon in our example changes direction somewhere within the patient. By changing direction, it loses some energy, as illustrated by a longer wavelength. If the change of direction is great enough, the X-ray will miss the film. This process is referred to as scatter, and the lower energy photon that continues on in a new direction is called a scattered photon. Number 29. The two processes we have seen so far both prevent the X-ray from striking the film. Any process that prevents photons from reaching some predefined destination, such as a piece of film, is referred to as attenuation. Scatter may not always lead to attenuation. If the scattered photon does not miss the film, we wouldn't consider it to have been attenuated. Absorption, however, is always considered to be attenuation. Number 30. The two photons shown here have passed through the patient and are striking the film. Since they strike the film, they have not been attenuated. They are referred to as remnant photons because they remain in the beam after the beam has encountered the patient. Notice that one of the photons has changed direction slightly, but has not changed energy. We will discuss this type of small-angle scatter later in this section. The other photon does not interact at all in the patient. It travels in a straight line completely through the patient. Number 31. Here are all of the processes discussed in the previous slides. Notice that the difference between the number of photons in the primary beam and the number of photons that had been attenuated is equal to the number of remnant photons. In the following slides, we discuss the mechanisms at the atomic level by which absorption and scatter occur. Number 32. Part of the remnant radiation is made up of photons that scatter at a small angle and do not change wavelength. These photons undergo a process called coherent scatter. As you know, an X-ray is made up of changing electric and magnetic fields. In coherent scatter, the electric fields influence the negatively charged electrons in an atom, causing them to oscillate. In this illustration, the photon coming from the left is about to interact with an atom. This photon is labeled an incident photon. When the incident photon interacts with the atom, the electrons that are bound to the atom begin to oscillate. Number 33. As always, a charged particle in motion has not only an electric field, but also a magnetic field associated with it. The changing electric and magnetic fields associated with oscillating electrons move away from the electrons in the form of a newly emitted X-ray. This new X-ray has the same wavelength and frequency as the incident X-ray, but it is emitted at a slightly different angle than the incident X-ray. Number 34. Coherent scatter does not occur often in the diagnostic imaging process. It occurs most in human soft tissue at X-ray photon energies below 30 keV. Since the average energy of a diagnostic X-ray beam is about 1/3 of the kVp, very little coherent scatter is experienced above 90 kVp. Note that at 90 kVp, the energy of both the incident and the emitted X-ray would be about 1/3, or 30 keV. At voltages below 90 kVp, a small amount of coherent scatter does occur, however, and results in degradation of the radiographic image. More likely photon interaction in the diagnostic imaging process is one that leads to complete absorption of the incident photon. This process, as shown, is called the photoelectric effect. The incident photon strikes an inner shell electron in one of the atoms of the patient. The photoelectric effect occurs when an X-ray has enough energy to actually knock an electron out of its shell. The incident or entering photon then ceases to exist. It gives all of its energy to the electron, which, having been ejected from the atom, is called a photoelectron. Number 36. How much energy is required to knock an electron out of its shell? The answer depends on which element and which shell. The energy required to knock an electron from its shell is the same as the energy with which the electron is bound to the atom, or its binding energy. It is convenient to measure this energy in units of electron volts, because the energy of the X-ray and the photoelectron are measured in electron volts as well. First, we notice that the higher the atomic number, the higher the binding energy. The binding energy of the K-shell electrons in hydrogen with an atomic number of 1 is only 13.6 eV, while the K-shell electrons in lead with an atomic number of 82 have a binding energy of 88,000 eV. Number 37. Second, we notice that the inner shells of an atom are more tightly bound than the outer shells. That is, the inner shells have a higher binding energy than the outer shells. You will recall from Lesson 1 that we have said that the inner electrons have less kinetic energy than the outer electrons. That is, the inner electrons are less free to move about because they are more tightly bound. We can say that the inner electrons themselves have less kinetic energy because the energy that binds them to the atom is greater. The K-shell electrons of calcium, one of the elements of which bone is composed, have a binding energy of about 4,000 eV, while the L-shell electrons have a binding energy of about 350 eV. Knowing the binding energy of the electrons in an element and the energy of the incident photon, we can determine the energy of the photoelectron produced in a photoelectric interaction. For example, in calcium, the K-shell electron has a binding energy of 4,000 eV, or 4 keV